All right, welcome. I'm impressed. It's 3:31 and everyone's seated and ready to go. Mathematicians are very punctual, so I like it. Today is one of those fun days where we get to celebrate one of our colleagues for all of the work that he has done. We've started the Hovde Distinguished Lecture Series last year to celebrate our distinguished and named professors every 5 years to hear about what they're doing and the accomplishments they've made. And this is really, again, a celebration of the work that Professor Shahidi's done. And so I'd like to introduce Professor Freydoon Shahidi, who works in the broad area of number theory. And Carl Friedrich Gauss, one of the greatest mathematicians of all time, is said to have claimed mathematics is the queen of the sciences and number theory is the queen of mathematics. And so one of the reasons for the centrality of number theory is it deals with the prime numbers, which are basic blocks of numbers, which may think of them as atoms of mathematics. Prime numbers are also studied in K through 12, a factor number, and how many primes can you rattle off. If you've seen all of Euclid's proofs, there are an infinity many primes. Distinguished Professor Shahidi has studied primes, albeit at a much deeper level, with immense theoretical abstraction. In particular, Professor Shahidi studies prime numbers such as the distribution via the L functions. These are metamorphic. See, I'm a geoscientist, so I'll say metamorphic, which is exactly not quite right. Functions of complex plane associated to mathematical objects, and more broadly via Langlands program. Edward Frenkel described Langlands program as a kind of grand unifying theory of mathematics, and Professor Shahidi has made a deep and important contributions to Langlands programs, and there is the Langlands Shahidi, so named in his honor. Professor Shahidi joined Purdue University in 1977 after getting his PhD at Johns Hopkins University and has spent his career with us, and we're very thankful for that. He was elected to as a fellow of the American Academy of Arts and Sciences in 2010, and he was the inaugural class of fellows of the American Mathematical Society in 2013. He has continued NSF single PI grants since 2002, and he has made tremendous contributions to both the field and to mathematics at Purdue. So today it is my distinct honor to introduce distinguished Professor Freydoon Shahidi to talk about L functions and Langlands programs.
Thank you very much, Dean Flesh. It was very nice of you to introduce me so generously. And I like to thank also Irena for organizing everything, and Johnny Brown, last but not least, for helping me with all the slides and everything and presentation. Okay, let me start. I'm going to start with, let me go to the first. As Dean Flesh said, prime numbers. I'm assuming that there are some people who don't know what a prime numbers is, so I'm defining it. It is as you can see, it's something which is only divisible by 1 and itself, and the list of primes between 1 and 20 is just 8 of them. And they are basically important in producing this building block, so every whole number, every natural number can be written as a product of these things in a unique way. And then I put it in words because I'm going to need to use this, that for every whole number n, there are prime numbers, p1, p all to pr, and then integers. These are all distinct. And integers e1 all the way to er, so that you can write this thing as product of p1, e1 times, all the way to pr, er times. This is very foundational. There are a lot of algebraic structure, and this doesn't happen. But fortunately, it happens for integers. Primes are very important. We know them, that they have a lot of application. They are used in cryptography, banking, credit cards, transactions, and so on. And we want to know that there are infinitely many of them. Of course, long time ago, Euclid gave a first proof of infiniteness of prime. What he did, he assumed there are a finite number of them, p1, p2 to pm. Then we cleverly define this new number, product of all these guys plus 1. This is not divisible by any of these primes, just naturally. And then there should be at least another prime p bigger than pm dividing n. And that contradicts the finiteness of primes that was there. So that was the first proof that was given by him. I'm going to give you another proof given by Euler, and that was the genesis of having Euler products. Let me start with a familiar equality for you. I mean, you all know, the one who took any calculus, that if you multiply 1 minus x by 1 plus x squared all the way to infinity, you get 1. Everything cancels off. So formally, you can write 1 plus x squared equal to 1 over 1 minus x. Now, plug x equal to 2. The left-hand side is unbounded. The right-hand side becomes minus a half, and this is naturally false. And the reason is that there is no convergence in other side. On the other hand, if you choose 1/2 and you plug it in, you can compute this sum, and it's just 1 over 1 minus 1 over half, and that would be 2. More generally, if you take any real number whose absolute value is less than 1, then the left-hand side converges to this thing. So this thing is convergent only if absolute value of x is less than 1. If you plug 1, then both sides become infinity. The right-hand side and left-hand side both become infinity. So you don't want to plug a 1 in here unless you expect to get an infinity. These are usually called poles of the functions. They are singularities. Now, using this identity, Euler proved, he lived 1707 to 1783, and he proved this thing, I think it was in 1737, in the following fashion. Remember this equality we had? Just plug in it 1 over p for x. Then you're going to get 1 plus 1 over p all the way plus 1 over p to the n all the way to infinity is equal to 1 minus 1 over p to the minus 1 by this. That's 1 over 1 minus 1 over p. Now, consider this for all primes. Multiply them through. Multiply them through. When you multiply this through, you will be having all these products of these infinite sums. And you will see that when you multiply them, you're going to get every combination of powers of primes multiplied by each other. As I said in the first page, when I talked about prime numbers, then that will give you a unique natural number, a unique whole number. So you're going to have this sum, 1 plus 1/2 all the way 1/3, 1/4, so on, 1 over n. And we know that this is unbounded. So this will tell us that product is unbounded, meaning that the number of prime is unbounded. So you have infinitely many prime. This was his argument, and that's where the name Euler products comes in. This product here is called an Euler product, as I'm going to be talking about next. This equality 1 that we looked at works for absolute value of x less than 1. To make it more meaningful and for the purposes that you will see later, it is a good idea to introduce complex numbers or variables. I'm going to be using two different variables. The one is z, and the other I is square root of minus 1, x plus iy, and s equal to sigma plus it. These are all real. X and sigma are real part, y and t are the imaginary part. Now, complex numbers, everybody knows how useful they are. They're useful also in applications. Electrical engineers, in courses we teach here, we do use a lot of complex numbers. And it's a lot more useful too in mathematics as well. Now, let's look at that. Let's go back. Remember, I have this sum 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. And I have these products 1 plus 1/2 plus 1/4 and so on. Let me, instead of putting 1 over p, put 1 over 2s. S is a complex number. Let's put 1 over 2s, 1 over 3s, 1 over 5s, and multiply them. So when I get, I'm just going to get, this is really 1. This is 1 over p to the s. When I multiply all of them, I'm just going to get, again, the same thing. All the combination of all the product of primes to the power s. This complex number is. You have a positive integer. Raising it to the power s is no problem. You just take you write it is 2 to the s plus sigma it. It would be 2 to the sigma times 2 to the it, and 2 to the it can be written as some combination of sine and cosine. So it is very easy to do that. You don't need to take any branch or anything. So this is a very natural sum, and you take it's equal to this product. And this is called the Riemann zeta function. This is the famous Riemann zeta function. It converges it converges, at S it explodes again. At S it becomes the same thing that we saw before, so it becomes explode. But if you look at other values, if you assume sigma is bigger than 1, then both sides of this converge. So this is a real equality. It's not a formal equality, but only for sigma bigger than 1. Now, in general, this happens with many of the L functions that I'm going to talk about. Now, let's see the behavior of this again. If you look at absolute value of p to the minus s, it is really p to the minus sigma, just to the real part. That's less than 1 over p, and that's less than 1. Now, for it, if it is less than 1, you will, already if it is this even, even if it is less than 1, that sum, as you can see, that sum here converges. Even sigma positive will work, but you really have an infinite product. For the infinite product to converge, you have to have sigma bigger than 1. So this thing, both sum and its infinite product, they both converge if sigma is bigger than 1. If you put sigma equal to 1, you're going to produce a pole. You're going to have an explosion. And then this is called the famous Riemann zeta function, which is, there are things attached to it. And I'm going to talk about it. Before I get to mentioning Riemann hypothesis, of course, it has not much bearing to my talk, but I'll mention it because it's an important problem. Let me talk about analytic functions. The complex plane has two variables, the imaginary and the real. The imaginary is usually the y-axis, and the real is the x-axis, the two-dimensional coordinate you see in calculus and everything. Now, so a complex plane is really like a R2, like a two-dimensional Euclidean space. And if you have a function in two variables, f of x, y, if you succeed to write it as a function of only one variable being this x plus iy, then this function is basically an analytic function. Of course, it is a local property, but this is a provincial good definition before I get into partial things or things which are not really necessary at this step. Now, if you look at the zeta function, it converges for all s, sigma equal to it, with sigma bigger than 1, extends to an analytic function. It behaves like that at every place except at s equal to 1. This is one of the objects of the program. If you have an L function, you have a zeta function, you want to prove it has a meromorphic continuation to the whole complex plane, meaning it is analytic everywhere. It will have some poles at a finite number of poles for our purposes. Now, these are the kind of properties that you want an L function to satisfy. So I just mentioned it in this case. The Riemann zeta function is exactly like that. And the famous Riemann hypothesis said that if your real part of S is between 0 and 1, then zeta is equal to 0 if and only if this real part, which is sigma, is equal to a half. This is a very difficult problem, and as we know, it's unresolved. There is Clay Institute has put $1 million on it. If any of you is interested, you can try, but believe me, you will have a lot of competition. And we just showed that there are infinitely many primes that in general. But one can ask question about what about primes of certain form? For example, 1 plus 4n, n an integer beginning equal to 1. More generally of the form a plus dn. Now, a and d are fixed, and n ranges over all the natural numbers. Here, a and d cannot have a common divisor. So a question is, if this is going to be a prime, then they cannot have any common multiple, because then that will come out and it will never be a prime. So it comes by the question that these two a and d have no common factors. Now, Dirichlet answered this question by using again Euler products. So these Euler products, so far that we have seen, is a product of 1 over polynomials over infinitely many primes, infinitely many places. So let's see what he did. He lived from 1805 to 19. What? That should be 18. We didn't catch that, Johnny, did we? That's 1859. Okay. Now, he introduced it's a Dirichlet character. It's a periodic function. It's usually a period. Period is denoted either d or m or whatever. So let me define it, give it the notation, its period is d. And then he defines a Dirichlet character is a function from non-negative integers to complex numbers. It is of period d, it will satisfy the following things. First of all, chi of product of two integers m and n is chi of m times chi of n, so it is multiplicative. It is non-zero if and only if m and this period d are relatively prime, meaning that they have no common prime factors. And finally, it is periodic, as I wrote in here. Then he considered this Euler product. He multiplied all this polynomial 1 minus chi of p over p to the s to the inverse. It's just 1 over a polynomial. He multiplied all of them, and he observed the analytic properties and proved the infiniteness of primes of this form, a plus nd, a and d equal to 1. It is using a very important property of this function, that it doesn't vanish at 1 for all chi. Even chi equal to 1, it becomes infinity. But for any chi, it doesn't vanish. And these non-vanishing theorems are very important. We also do it in the theory of automorphic forms, and I have a theorem which implies this in a large number of cases. Now, things will pick up. So let me get a drip of water. Any questions so far? Any new proofs of? All right. Eisenstein lived very short. As we noticed, I think Dirichlet lived very long, but he lived very short, only 29 years. And to introduce what he did, one of the things that he introduced to number theory, let me denote by H, German H, upper half plane, everything of every complex number for which the imaginary part is positive. Then let's look at this group, gamma. Gamma is SL2Z, all the 2 by 2 matrices with integer entries. So everything is an integer, and its determinant is equal to 1. Usually when you have matrices, you say they are invertible if the determinant is non-zero. But since you want to stay inside this thing that the inverse also has integer entries, you will either have to have determinant equal to 1 or minus 1. So we take the 1 with determinant equal to 1. Now, if I take Z in H and gamma, a matrix in gamma of the form A, B, C, D, these are integers, you can define a fractional linear transformation in the following way. We say gamma acts on Z if sends Z to AZ plus P over CZ plus D. This is some form of Mobius transformation. It is very important in the theory of modular forms. Now, what Z, the fact that it sends Z to a gamma Z, Z is in H, so it's absolute, his imaginary part is positive. You can easily show that so is gamma Z. So it's really an action. It sends something in H to something in H. Let me introduce this subgroup, which we need to get rid of. It is plus minus the matrix 1, B, 0, 1, 2 by 2 matrix. B is an integer. And notice that the linear, fractional linear transformation action of this on Z is just moves, shift Z by B. That's all it does. Now, Eisenstein's series is in the following. It looks very nasty. There are all these imaginaries. You take imaginary of gamma Z and raise it to the power S. This is some complex number in upper half plane. You take its imaginary part. It's positive, so you can raise it to the power S. And if you put it in that, if you make this explicit, imaginary of gamma Z is just imaginary of Z divided by absolute value of CZ plus 2 squared. So this is the explicit formula, runs for all C and D which are relatively prime to each other and C and D integers. Now, in this side, you have a sum over SL2Z. This would be a very explicit formulation, but it's not as useful as this one. You have a sum over everything in SL2Z, but you want to get rid of this because you notice that if you look at imaginary of this action, is imaginary of Z plus B. B is an integer, so it's just imaginary of Z. So when I put something in B2 of Z, that argument doesn't change. So if I integrate over B2 of Z, I'm going to get infinity. So I would get rid of that. So I divide out by B2 of Z. This means that for every group I have element in SL2Z, we choose one up to this guy. So we get rid of this B2 of Z. Now then, we get this sum converges for real of S positive. It's not even easy to prove in these simplest cases that the Eisenstein series is convergent. It's a difficult proof, even in the simplest cases, GL and GL2. So now, again, if you notice, E of gamma Z is equal to E of Z This is for all gamma and gamma. You can conclude that E of z on S is a function on H mod gamma. H mod gamma means that I'm looking at things under this action of gamma, meaning that if I take something, and if I take this z and change it by something in gamma, it doesn't change. So it's really a periodic function vis-a-vis this subgroup gamma. You have a periodic function. The first thing comes to your mind is a Fourier series, a Fourier expansion for this. Now, these guys are pretty nasty. You look at their Fourier expansion. The reason is that these guys are not analytic. The way I define this Eisenstein series, they are real analytic. What I want you to concentrate on is this part. This whole thing is the constant term. I mean, you have a Fourier expansion, you will have a constant term, and for every integer, you will have another term, and so on. I want you to concentrate on this, and I want you to concentrate on this. Don't worry about this one. This is easy to. And also look at this one. This is a complicated function. It is given by this formula, twice of square root of y, which you can do because y is positive. And then this is K-Bessel function. I give you the formula here. You don't worry about this thing, but look at this. When you do that sum, you're going to get some exponential of 2 pi I n x. So it is not complex analytic, but it is real analytic because the variable x will show up in this sum. And this is called the real analytic Eisenstein series. There is a holomorphic Eisenstein series, but these are the ones which would be of interest to me. Of course, I'm interested in all the holomorphic forms, but these are the ones when they are unsolved problem about. Okay? Let me, one object which in Langlands program shows itself over and over is that you will have to have products over primes. Just as we saw in the proof of the first proof of Euler, we saw that there is a product of primes. So, and when you are talking about primes, for us, there is infinite prime, which is Archimedean place, and there are all these other primes. I'm going to talk about how these primes, contribute to the theory. But it is important to think about these things as products. So we define these are, remember, these were 1 over polynomials that showed up in the Euler product at the beginning. We put 1 from infinity. This is, we take pi to the minus s over 2, gamma of s over 2. Gamma is a gamma function, the function which generalizes n factorial or so on to the complex plane. Then I will define L of s. Now it is the product of all the local L functions for every prime and infinity prime. So it just looks like this. Okay? Now let's go back. Look at this. You have this and you have this. You have also this. Now, if you look, okay, if you look in here, the constant term can be now written by this formulation. The constant term is y to the s, L to the 2s minus 1 over L to the 2s, y to the 1 minus s. Now, for the non-constant term, you basically will get also 1 over L to the 2s. Now, L is this completed L function. Now, if you use this thing and functional equations of the Eisenstein series, you can prove the functional equation. This is something difficult. Functional equation for the Riemann zeta function. Okay, this is another proof of that. Now, one of the big things that you will see as I go on is generalizing this theory of Eisenstein series. To understand the theory of holomorphic forms, you have to have Eisenstein series in general because you will have a huge L2 space and you have to decompose it and you have to get rid of its continuous spectrum. The only way to do that is to study Eisenstein series. And Langlands did that. He wrote a huge manuscript before he even thought of the Langlands program, developing theory of Eisenstein series for a general group, arbitrary reductive group. He did it. And now, let me go to the last example. This was a continuous object. This will appear. I'm going to talk about all these things. But now let me talk about the discrete object. Hans Maas, he lived a long life. I think he passed away in 89 or something. And he introduced these Maas-Kaas forms. And one thing about it is that if you look at all these things that we have, we look at SL2R, we looked at h over gamma, all those functions that we have are square integrable. This is a finite volume, and then there's a measure. You can integrate a function, a square of a function, and all these functions are the Eisenstein series and all other ones are in here. So they are in L2 of H mod gamma, you will find no, as you can see, you will find no analytic function on H which is invariant under gamma, except for constants. The only functions on H which are invariant under gamma are constant. If they are analytic, they are constant function. What Moss did, he introduced non-holomorphic form. He introduced real analytic forms. And now the cost form means that the constant term is 0, introduced these objects which appeared in L2 of H mod gamma. And they are really functions. I mean, they are modular forms. Those are forms. Those are differential forms in this sense. But I mean, as a function, this was the only example. Now, these functions can be very nicely given. Again, it has a Fourier expansion. It will look like this, f of x plus iy. Remember, it's a function on z. This is, again, a square root of absolute value of n to the y. An is the Fourier coefficient. It's some complex number. This is, again, k-Bessel function. Let's not worry about it. And again, you have exponential of 2 pi I n x. You realize that the expansion in this second variable is like coefficients of this exponential. Then again, this is not a complex analytic. It's a real analytic function. Okay? Now, these functions, these examples that I'm giving you, they are they are eigenfunctions for hyperbolic Laplacian. Hyperbolic Laplacian is just like this, minus y squared, second partial with respect to x, and second partial with respect to y. If you're working with the Euclidean space, you don't have this y squared here. But when you have this hyperbolic space, these are Riemann surfaces, on them you have these. You have these operators, and these functions are eigenfunctions for this guy. And then there is the eigenvalue. If you look at the formula here, there's an S. Eigenvalues for this operator can be written like this, 1/4 of 1 minus s squared. There's a reason that we do that. And again, there is no constant term, because this is a cost form. The way it was developed was that he assumed that there is no constant term, and he developed them. If there is a constant term, you will have those Eisenstein series we just talked about. All right. There are these Fourier, so if you look at this formula, everything is there. Everything is explicit except for these coefficients. The questions are, what are these coefficients? What are these Fourier coefficients that are showing up any information about them? And that's, of course, very deep. And there are conjectures. One of them is the Ramanujan conjecture. It says that for all the primes p, this Fourier coefficient, this AP, must be of absolute value less than or equal to 1 over square root of p. And there is also the Selberg's conjecture. This tells you about the smallest eigenvalue, lambda of delta. It says that it must be bigger than or equal to 1/4. And if it is bigger than or equal to 1/4, 1/4, 1 minus s squared bigger than to 1/4, implies that minus s squared is bigger than or equal to 0. And this will tell you that s is pure imaginary. Now, these two conjectures may look stupid in a way because it doesn't give us the Fourier transform, it gives us some bound. But what is special about it, as I progress later, is that these things really imply that in representation theory, the matrix coefficients at the places when the Ramanujan is valid, they are tempered. The matrix coefficients behave nicely. So these are not just some stupid conjectures we have here. Peter Sarnan considers these two conjectures in par with Riemann hypothesis. So far, we haven't been able to do them, but we have done much better. We have got not short, but very good estimates for these things, which I will explain at the end of my talk. And they have all come from the contribution that I have made. Now, let's start with Robert Langlands. Langlands, he retired, I think, 10 years ago, and he is now in Canada. He's a professor emeritus at the Institute for Advanced Study. He used to have Einstein's office. That's where Einstein was. And he really produced these programs. And I got to meet him the first time when I went to the Institute as a postdoc, 1975, 76. And he was very nice. And he talked a lot with me. And he put me in a direction that became pretty much my career. And let me then move on to tell you what is the program. He wrote a letter to Andre Weil. Andre Weil was the greatest number theorist of previous century. He was at IAS. He was at the Institute. 1906 to 1998. When he was getting older, he was getting nicer, and I had lunches with him. It was very pleasant then. And he proposed a connection of problems and conjectures. And it was the beginning of the so-called Langlands program. They all appeared in a very famous paper, Problems in the Theory of Automorphic Forms. Now, this is just before he did that. This is before he did that big manuscript concerning the Eisenstein series. Now, this program by now has proved itself to have incredible consequences in arithmetic algebraic geometry. I won't be able to say much about this in representation theory, automorphic forms, and even physics through geometric Langlands program. Now, this, as I said, this massive manuscript that he wrote was the beginning of the program. In fact, program was proposed after that, but this was central in developing it. Now, let me go back to those things that we had. We had Eisenstein series and we have Moss forms. These are examples of functions living in L2 of H mod gamma. Gamma equal to SL to Z. Before I go any further, is there any questions about any of this? Laszlo? Okay. It has been easy then so far. Now, if you look at H, I went too far. Okay. If you look at H over SL2Z, H really itself is SL2R divided by this compact subgroup, cosine, sine, minus sine, cosine. This is a very nice. I mean, it doesn't make much difference in what I want to say, and you can write H over SL2Z to be equal to this object. This is an example of a Shimura variety, the simplest, lowest dimension Shimura variety in some sense, which is very important to algebraic geometers and arithmetic algebraic geometers. I mean, there are conjectures about Hasse-Weil zeta functions of these things very generally, and one of the applications of Langlands program is to prove the conjectures of Hasse-Weil about this Shimura variety. So this is just the simplest example. This SL2 is SP2, so that's why it is. Now, one thing you want to do is you want to study this L2. So you want to study, instead of looking at L2 of H mod gamma, you want to study L2 of SL2R over SL2Z. What does this to you? It gives us representation theory. It gives us analysis. It gives us a lot of tools that we didn't have before. We only had algebra. Now we're going to have some number theory, which was just a bunch of formulas. Now we're going to have tools which are not just formulas, tools that can prove things. Now, when you want to study this SL2R over gamma, gamma is now SL2Z, you really have to, to cover everything, you have to get gamma to run over all the so-called congruent subgroups. I'm not going to define what they are. They are particular subgroups of SL2Z. Now, then you have to take their union. You have to take the union or to take the direct limit of these things. So you have to study every L2 over SL2R over gamma and then put them together. A better way of doing this, of course, let me just tell you that holomorphic modular forms have played a central role in the proof of Fermat's last theorem by Andrew Wiles. I remind you, Fermat's last theorem was to prove that a to the n plus b to the n equal to c to the n has no integral solution with all the things non-zero. A, B, C should be non-zero. And you just think about it. For 2, you can do it. 3 squared plus 4 squared is 5 squared. The same with 6 and 8 and 10. So you can do things like that. But as soon as you go to n equal to 3 or higher, nothing happens. You can't do it. And Fermat claimed that he can do it in this margin of the book, and this is too small, he can do it. And he made everybody crazy. People worked on it for 300 years, developed all kinds of mathematics. Finally, Andrew Wiles proved it using very complicated, modern stuff like these connections, the Shimura-Taniyama conjecture, pretty difficult stuff. Now, so this means that study of this space is very important. At least I try to convince you in this fashion. And the program itself played a central role. One of the things that I will talk about is the symmetric square lift due to Gelbart and Jacquet, and that played a central role in the proof of this thing. Now, to really study, instead of going to these limits over all the, congruent subgroups, a better way of study is to look at a different group. The better way is to understand and introduce the so-called adels. Now, adels is an infinite ring. It's a product over all the QPs. QPs are just completions of Q with respect to periodic absolute values. Now, when you have this object is locally compact. You can integrate. You cannot integrate over Q. You can't do anything. So this gives you a big dimension. Now, let me just quickly tell you what adults are. The periodic absolute value is like this. If you have a rational number, Q is rational numbers. R over S, its periodic absolute value is just P to the minus M. And how does M come? M comes from here. You write R over S and R prime over S prime, sum P to the sum power M. And you want this to be the largest thing appearing. So these guys are not divisible by P. And then you have this absolute value. It just behaves like the absolute value, normal absolute value that you know over R. I mean, x plus y is less than or equal to x absolute value of x plus absolute value of y. And the same thing is true. It's even better than that. But then after you have this is usually called QP. You complete it. You take Q and you complete it with respect to this. You fill up the holes. Just when you have Q and you have R. There are these emptiness in between. I mean, Q is discrete, R is continuous. You fill up these emptiness by taking completion. And you can do the same thing. There is using Cauchy sequences and so on, but let's not get technical. And then you look at this infinite product. This is not a full infinite product. For almost all the places, these are for each prime you have a component. And for almost all of them, I want the absolute value to be less than or equal to 1. And of course, we don't worry about x. We can't say anything about x infinity. Just leave it. Anything in R is fine. X infinity is R, real numbers. You pick anything at the real places. But everywhere else, you make sure that almost all these absolute values are less than or equal to 1. Then this is called a restricted direct product. It's not the full direct product. And this will be a ring of, there's a lot of interest. As I said, it's a locally compact ring. And you can do a lot by looking at this. Now, let me define, first of all, the ring of integers. ZP is the ring of integers of QP. And it's the direct limit over, this direct limit over all the congruence subgroups would be better understood if you look at GL2 of AQ, all the 2 by 2 matrices with entries in this ring AQ. Just take a 2 by 2 matrix, just plug in these infinite products as entries. And of course, we want it to be invertible. That's the definition of GL2. For that, it means that its determinant should be a unit in AQ. Now, this group acts on the functions. You take a function f, you take a variable y, you take a right translation by this variable y on f. So this is a new function defined by f of xy. X and y are in GL2 of AQ. And this will produce for you a representation. What does a representation mean? You have a group, assume it's just, and you have a finite dimensional vector space. To every element in the group, attach and attach a linear transformation of that space. Just a matrix if it is finite dimensional. All that you want is that if you multiply 2 elements in this group, what is the corresponding linear transformation? It's just a composite of those linear transformations. This is called a representation. And then these spaces that we have been looking, this L2 guy that we have been looking, is a representation because of this action, by this action that I put in here. Now, this is a huge space. You want to go to its nucleus. You want to go to the smallest pieces, non-trivial smaller pieces, and on which this group acts, keeps it invariant and acts on it. So those are called irreducible representation. You will have a direct integral, and you will have a direct. So all the bad things happen in this space. It's really huge. Eisenstein series are there to understand this guy. And these cost forms are there to understand this part. There's, of course, one more extra things. The residual, but let's not worry about that. And these irreducible sub-representations are called automorphic representations. Functions in this space are called automorphic functions. And the reason that it is called automorphic because of the invariance under GL2 of Q. All right. Now, these Eisenstein series and they appear in the continuous spectrum. Mass cost forms appear in the discrete spectrum. Look at an operator, it has a spectrum. And if you take a mass cost form, for example, it's an eigenvalue for this hyperbolic Laplacian and all the periodic analogs, which are called Hecke operators. Now, if you take one of these functions and let the group GL2 of AQ act on it, it gives you an irreducible representation. So that's one way of producing irreducible sub-representation. Now, Langlands program is a study of automorphic representation, not only for GL2, but for other reductive. Reductive group is a subgroup of some GLN. GLN, SON, or special orthogonal group, symplectic group, alternating group, or exceptional groups. They're twisted and inner forms, whatever you like. These are reductive groups. And Langlands' program was to study automorphic forms for all of these. And he has a fundamental conjecture which relates them to each other on different groups. One of the main quests that Langlands had, this was, I think, just before. He was at Princeton, and then he went to Berkeley, and he came back. This was really 1966. For years, he wanted to generalize the notion of an L function or a zeta function. He made many attempts, and he did not succeed to a level that he was thinking of quitting math. There is an interview with him by Julia Muller. We have a volume called The Genesis of Langlands' Program. The interview is there, too. And in there, he says it. He says, I was thinking of quitting math because I couldn't find the definition of L functions. Then when he comes back from Berkeley in the summer of 66, he sits down and computes the Fourier coefficient, the constant term of the Eisenstein series, this theory that he developed. And he ends up seeing a lot of ratios of L functions, and not the L functions, but the Euler product, just like this. And then he wanted to understand what are these? How are they defined? For that, he had to introduce something which is called an L group. You have a group, you have GLN, you have GL2, and you want to define something called an L group. This is a complex group. For GL2, it's GL2C. For GLN, it's GLNC. And it has a dual data to the dual structural data. Those of you who have seen Lie groups, you know that the dual to SO2n plus 1 is SP2n, and then you take its complex points. So this is the L group attached to this group. GLNC is the L group attached to GLN, of course, GL2C for GL2. And how did he define Eisenstein series? He started going to some smaller subgroups called Levy subgroups. These are special. And he took cuspidal automorphic representations on them. So these are in L2 of M, L2 of M of AQ divided by M of Q. And they have, the constant term is 0. He put things on there, and then there is a way, he just sums up, or a way of inducing them to the group. So Eisenstein series, that's the simplest way of relating a representation on something smaller to the big group. So the smaller group is M. You take an automorphic cuspidal form there, and you go through a machine, and you produce it. What he noticed, that not only he would need to introduce this L group, he would notice that in these calculations that it is, there are finite dimensional representations, Rj, of this LM guy, of this Levy subgroup. And then he could understand what the Euler products are. This led him to define what is the general L function, and is the foundation of his letter to André in 1967. And it's also his calculations were the starting point of our method. Now, so let me start. I have to still define some objects, then I can tell you what is it and what has been done. If you take a cuspidal representation of M of A cubed, this was the one that gives us the Eisenstein series, then it will be really a product of representations of local groups. Pi sub p is a representation of M of qp. This is, the whole nature of this program, that everything is a product. Then he looked at, there are these unramified representations. These are there were infinitely many things when pi was product for each p. And he noticed that all but a finite number of them have a condition that there is a vector in their space which is invariant under M of Cp. So pi is a tensor product of problems of the local representations, pi sub p. He noticed that it's easy to see that for almost all of them, these pi sub p's have a very nice property. They have a vector in their space. Remember, there was linear transformations coming from this group M of Zp. That's a compact group. And this thing acts on these things trivially, meaning that there are vectors which are fixed under the multiplication by this M of Cp. He called them unramified representations. And then there is a Sataki's work which tells us that unramified representations are parameterized by semi-simple diagonalizable conjugates, just by diagonal elements. In GL2, these unramified representations are given by the diagonal elements. Something in GL2C, diagonal elements in GL2C. Then he could define the unramified L functions. L functions attached to this guy. You have an unramified representation. You have the corresponding conjugacy class. You have a finite dimensional complex representation of this Lm. And you have a complex number. Then you define this L function. It is a determinant. I, this is identity of size of the dimension. This is a GP, I mean R of GP. This is a representation of, again, this dimension, the same thing. It's a, and then this is a matrix of that dimension. You multiply everything in that by P to the minus S. You take the determinant and you invert it. The choice of the element in the conjugacy class is irrelevant because it comes out of the determinant and cancels itself out. So this is the unramified L functions that he defined. The simplest example is the Dirichlet L function. You can just get it out of GL2. The Levy is GL1 cross GL1. The representation is just you put a chi in here and 1 in the other GL1. This is an infinite product of the characters. And then GP is just the value of this character at P. And R, the representation is just multiplication by GL in GL1C. And the L function that you get is just the Dirichlet L function. What he noticed that in constant term, those Euler products that he was not able to understand are really this. Just product over all the unramified ones. Of course, there are other pieces missing, but if you assume everything is unramified, then the ratios of these L functions. There were these M representations, R1 all the way to Rj. M depends on G and M. The local representation, pi p, and the complex argument here is Js and 1 plus Js. The ratio of these two L functions appears there. So he finally understood what these things are. Now, what does the method do? For example, it generalizes and defines these L functions at all other primes. I said these are only for unramified, but the complication is for the rest of them. And you have to define so-called root numbers because you will need them for the functional equation. If you remember functional equation for the Riemann zeta functions with L of 1 minus S equal to L of S. In general, there will be some constant of, L of S would be some constant epsilon times L of 1 minus S. And those are very subtle. And to define them, you have to define local root numbers. And so these were all defined. It proves the functional equation and establishes their analytic properties that one was interested in. For those, by looking at both constant and non-constant, and of course you want this non-constant term, those which are Fourier-Whittaker coefficients, those things to be non-zero. But this can be generalized. There are nice conjectures that can generalize them to any representation. Now then, it establishes equality of local L functions and root numbers. The part that I said I'm not going to talk about is the connection with the Galois groups and Galois representations. These representations can be parameterized by Galois groups, by representations of the Galois groups. And then there are representations of the Galois groups, and to them there are L functions and root numbers, and these are called Artin factors. And we proved a good number of them, that the ones that we define, which are defined by harmonic analysis, are exactly the ones that is defined through the Galois representations of Galois groups. So this is number theory. So we connected these two to each other. In conjunction, I'm just going to say a few words after this. Conjunction with converse theorems of Cogden and Piasecki-Shapiro, we prove striking cases of Langlands functoriality conjecture, which I'm going to talk about right after this, and that will be the end of my talk. This leads to new and far-reaching estimates toward the Ramanujan and Selberg's conjecture, applications to number theory and representation theory, applications to Arthur Selberg's trace formula by taking care of the local intertwining relations. These are important in his work. Now, let me talk about functoriality conjecture. This is one of the biggest pillars of the program. This is just an amazing conjecture. It's very difficult. Let me tell you what is it. Let me formulate it. Remember Eisenstein series. Just transfer the automorphic forms on the Levy to the full group. Now, functoriality principle or conjecture is a far-reaching extension of that. You need two groups, as I said, relation between automorphic forms and two groups, G and G prime, two reductive groups. You have a automorphic Cauchy-Vidal representation, let's assume it's Cauchy-Vidal, of G prime, this G prime of a Q. this L group of G prime to L group of G. Then I went and I found all the unramified representations on the other one, and I looked at the. Okay, good. Remember, I find the image of G prime of P under this homomorphism phi, and then I looked at inside L of G. This gives you a conjugacy class, and I found the unramified representation. This is like which was attached to it. Now the conjecture says that there exists a homomorphic representation part, this one of the big group of G, so that this traces is this one that I defined. So twice of T that I defined here. So you have it, which appears in and almost all the places it is equal to the this homomorphism. This is extremely deep. I'm showing something appears in L2 of G divided GL2 of AQ divided by GL2 of Q is very deep, very hard. As I said, this is a very deep conjecture, very fragmented cases. One of the most interesting cases of it is the so-called symmetric power cases. We take a positive integer n. First group is GL2, the second group is GLn plus 1. Of degree n in two variables. This is a homogeneous form of degree 1. And let's look at change the variable from xy to xy times g. This is a 2 by 2 matrix. Gives you a new polynomial. Look at the coefficients in here and compare it to the coefficients in here. There's a now, there are n plus 1 coefficients in a form of degree n in two variables, and so it's going to go to a GLn plus 1 of C. Now, this is a homomorphism. This is a complex map gone from the GL2C to GLn plus 1C. This is called the n-symmetric power, and this is called the n-symmetric power representation of GL2C. If we know all these things, we can prove all pictures, But let me tell you what we know. We know that this is sim n exists, it's automorphic, and in that the curve equal to 3 and 4 by the method, and in 2001 Kim, my former postdoc, is a professor at Toronto now, and myself, we proved it for n equal to 3, and soon after I told him, and he went and did the case n equal to 4. Now, as I said, these are far-reaching estimating Ramanujan conjecture. There is also transfer from GL2 cross GL3 to GL6. This is also quite a bit of success. This gave us a GL3, and then there is this transfer from classical group to GLn. This is also proved by Arthur in the case when the representation is general. And there is a transfer from GL4 to GL6, which is due to Kim, and that gave him the sim4. Then, saying what is the path forward? Extend to infinite dimensional groups. There is a big general program that hasn't gone too far yet. There is another one trying to establish functionality by other methods. There was an idea of Langlands in 2000 called beyond endoscopy, and then there are other approaches to L functions, Brogdon, Kajdan, Engel. L functions, you know all the L functions, and you know all the functionalities because you have found this. But without. And then finally, then G is different from GLN, ranking several should may not be true. As I said, I mean, the matrix coefficients and we are working on it and then of the method, special values of L functions. This is something that we're doing with Raghuram and my student. There's a lot more to say, but I think I took more than 15 minutes. Thank you. Oh, there is one more thing.
everyone.
Two, three, four functorial disprove. So what is the nature of the difficulty that arises when you try to pass to 5, 6, 7?
So the Langlands Shahidi method uses to prove up to n equal to 4. Beyond that, there are only a finite number of exceptions. There's the conjecture. You solve the existence of the power. That's by that going to infinite dimensional cases. Because there are infinitely many groups, you can prove a lot of stuff, you can have a lot of L functions, and then you can apply the converse theorems, and you get all of these guys exist. And the same thing with the next thing that I said, if you get all the L functions, this approach of Braverman and Kajjan, and then again you have all the L functions, again converse theorem will prove everything. But we don't have it. So there have been attempts to do that. There's also using trace formula, and that's what Langlands was tried through this beyond endoscopy, and that's also very, very elementary stages.
Anyone brave enough to use the mic? Another question? All right. Well, please join me in thanking Professor Shahidi one last time. This was a wonderful talk. Thank you.